Okay, you can go ahead. Thank you.
Okay, thank you. So as I said, Wynn Jacobson-Galán is here. He was starting the week visiting us, and next week he will be around. So if you want to talk to him, he's in his office. And today he will talk about the panchromatic picture of red supergiant liminality.
Yeah.
Okay.
Okay. Hopefully that's not a problem. I'll fix it if it is. Yeah, thank you, Claudia. Thank you, Luis, for having me. I'm Wynn. I'm a postdoc at Caltech, and I work on everything kind of related to what red supergiant stars, so one of the most common supernova progenitor stars between 8 and 20 solar masses, do right before they die. And I just wanted to talk to you all day and share some results about what I'm doing and my group is doing at Caltech and students have done with me. And so, yeah, let's get into it. So my title has a funny word in it, liminality. I only really learned about this word recently, and maybe it's good for grants because it looks a little, fancy. Liminalidad is what it is in Spanish, but it kind of means this transitional space. So it means the in-between or ambiguity or influx. Sometimes I feel like I'm in liminality most days. But I think it's a good application to stars because it's this space where a star is about to die and it is going to die, and it's in this in-between space that we don't understand. And stellar evolutionary models can't predict quite yet, but we can use their explosive deaths of supernovae to constrain what is this transitional space. Why do stars die? How do they die? And what are they doing right before they die through supernovae? So my ultimate goal as a researcher is I use Panchromatic, multi-wavelength, every photon, radio to X-ray. And I'll talk about all those wavelengths today to build this comprehensive picture of what red supergiant stars do right before they die. So this is years, months, decades, century. We'll go from days all the way up to centuries and millennia in this talk. Okay, so that might be a problem, but at the top is kind of a timeline. So this is time before explosion. Maybe I should get rid of all this. Yeah, it's my problem.
You can click OK in the compile. Yeah.
Okay, perfect. Okay, so this bar will be up there the whole time. It's like a time before explosion. So every time the red supergiant is at a certain phase, that is what the observations that I'm showing you are actually mapping. Because as a star is getting ready to die, it's this is not. Right. So yeah, as a red supergiant is getting ready to die, it is ejecting material. This material is formed at circumstellar material, and this is the time before explosion. And this material is liberated, so it's moving outward in space. And as soon as the supernova goes off, it will then collide with that material, providing a time machine back to when this star was actually ejecting this material. So as this star, in its final burning stages, is ejecting more material, it starts to get a little bit more tumultuous, we think. This is all kind of like theoretical, but I will hopefully support this with observation. And the time before explosion forms a circumstellar material. It gets more and more violently ready to explode. And then at T0, it explodes as a supernova. And so the supernova then creates a shock wave that moves outward into space. It is the star that's now liberated. It then moves outward in space at a characteristic velocity, 10,000 kilometers per second or so. And then it interacts with slow, cold material, which is the circumstellar material. This was stuff that used to be on the star's surface. Now it's freely floating in space. But that stuff tells us what the star was doing right before it died. So as the supernova, interacts with that material, then it can then provide electromagnetic signatures that then can tell us what the star was doing at different stages of its life, depending on how old the supernova is at that time. Because it's the supernova shock velocity is just how far is expanded over the time that I observe the supernova. And so this confined circumstellar material, this CSM around the star, is a really nice probe of the late stage burning phases of a red supergiant. Because so in our stellar evolution picture, we have different times before explosion, and these are the different elements fused at different stages. So we usually think about red supergiants as burning helium in their cores because they're now very inflated and they're big stars. But if I were to observe a red supergiant in the last 1,000 years before it explodes, it's actually burning core carbon burning. Then it's going to core oxygen burning in the last, almost a year or so. And then in the last week, it's burning silicon before it core collapse. So all these phases are inaccessible because for red supergiants in our Milky Way, because they're not blowing up, they're not exploding. But the red supergiants in other galaxies are exploding. And so then I can sample these phases of space of red supergiant evolution. And by seeing what the red supergiant explosion, the type 2 supernova is doing as it expands into space. So the time before explosion that I'm looking back at is just the time of the supernova that I observed, its shock velocity, how fast it's expanding, over the wind velocity, which is the material's velocity from the surface of the star. It's usually about 20 kilometers per second, which is the typical red supergiant wind velocity. So for a typical red supergiant explosion and its wind velocity, I can sample the final decade, the last 10 years of a star's life, by just observing a supernova within the first week. So you can imagine if I observed something within the first hour or the first day, I could have sampled the last year of a red supergiant's life. So that's kind of the first picture that I want to get into. So before a star dies, there's a couple ways that we can try to understand what it's been doing. One of which is literally just taking a picture of the red supergiant and then seeing that it went off as a supernova. So sometimes in nearby galaxies, we'll get a nice nearby type 2 supernova that comes from a red supergiant. We'll look back at archival imaging from an HST and now JWST, and we'll identify the star that actually resulted in that type 2 supernova. And so this is 2025 PhD. This is the first time that we've ever had JWST imaging of type 2 supernova progenitor. So we saw the red supergiant in JWST imaging versus the last 20 years, we've mainly just been working with Spitzer and HST. So this opened a whole new avenue for understanding red supergiants because we're sampling the infrared at longer wavelengths. And red supergiants are very, very interesting at longer wavelengths because they're cool hot stars, or cool big stars. So what have we learned from the detection of type 2 progenitors? Well, one of which is that they pulsate very dramatically in the last, decade before they explode. Red supergiants already are known to pulsate. This is the light curve in gray of Betelgeuse. Betelgeuse has a pulsational period. It might even have a couple overtones because it has a binary. But its general mode of pulsation is pretty dramatic. But then this is the pulsation period and pulsational amplitude of the progenitor of 2023 ICE-CSIC, which is a type 2 that went off in a nearby galaxy. And this is what its progenitor star was doing before it exploded. It then exploded over here. Huge amplitude pulsations compared to what red supergiants do in the Milky Way. So this is something very dramatic, must mean something very enhanced was happening, and is something that we didn't know until just recently. Secondly, we now know that red supergiants are even dustier than we thought. These might be the most dusty red supergiants we've ever observed, and they are the red supergiants that are observed before explosion. We look at the red supergiant dust composition and its infrared excess of red supergiants in the Milky Way and in local group galaxies, and they're nowhere near as dusty as the red supergiants that we are observing before explosion. So this is the first JWST SED, so this is the wavelength versus flux of the red supergiant progenitor responsible for this supernova. And without this mid-infrared coverage, we would have no idea that this is actually, a carbonaceous grain dust component, and it extends out to mid-infrared wavelengths and is this dusty. So a red supergiant with no dust would have a much bluer SED, but this is a much redder, very dust extinguished SED. And so this is dust that's in the local environment. This means the star was ejecting material. The dust then forms in the circumstellar environment and enshrouds this red supergiant. And so that's really essential component, probably related to these pulsations. And so this is the driving of material off. That material cools down, forms a lot of dust. This is something pretty essential about red supergiants that we're just learning. And as just a reminder, this is all happening in the last year to 10 years before explosion. The last thing I'll say about red supergiants through direct detection before explosion is that some of them are so luminous that we can detect them in pretty significantly distant extragalactic galaxies at super Eddington luminosities. So luminosities that mean that they are literally all definitely ejecting material because they are no longer in hydrostatic equilibrium. This is the first and only precursor of a type 2 supernova, 2020 TLF, where this is the progenitor star actually detected in not even that resolved of an image, this is a pan-STARRS image, of a galaxy at 40 megaparsecs, but it was so bright before explosion that then we actually detected in the pre-explosion image the red supergiant at super Eddington luminosities, meaning that it was likely liberating and ejecting a lot of material, whether that's from these pulsations that are super dramatic, maybe it's something more related to binarity or some sort of violent core instability that ejects a lot of material. But this is one example that was so bright that we actually observed it in just a ground-based image before explosion. And so we're looking for more of these. And so these are called supernova precursors. We usually detect these in more exotic supernovae that come from stars that interact with circumstellar material for a very, very long time. We think that maybe 25% of all supernovae that are strongly interacting, meaning that the progenitors ejected so much material that they're slamming into circumstellar gas for many, many years. We think that maybe 25% or more of them have these precursors. But it's super uncertain because these are pretty low luminosity events. These are just this is pre-explosion. And then the supernova goes off here. And this is in the last year or 2 years before explosion. And these are pretty low luminosity transients that we would have no real reason to pick out of a data stream because they look like just flat light curves, whatever. But I think in the future, this is then a connection to all of these possible mechanisms for powering super Eddington, but low luminosity events of a star right before explosion, and could lightly connect to why so much of the envelope has been ejected before explosion. So there's some leading theories about how we actually power these precursors, some of which have been kind of ruled out by observations, one of which is just put a bunch of energy at the base of the stellar envelope. It's more than the binding energy of the envelope, blows it all on. Will it retain any of the envelope? We don't know. This is super basic picture. You can maybe transmit some of the gravity waves from the internal burning out to the outer envelope. This has been kind of disproven recently because there's not enough energy to liberate very much material. So it's a possibility, but unlikely. You have this kind of like super Eddington wind that comes from a lot of transitions of metal lines at the surface of the star. This is probably something that very, very big stars do, so unlikely to represent a very large population. And then there's binarity. So this is some sort of common envelope interaction, unstable mass transfer, and then you eject a bunch of material. And then this would look like a very luminous transient. And so this is kind of a 3D simulation slice of ejected material put at the base of a convective envelope. So this is very active, but the ultimate goal with precursor emission is, can we predict supernovae? In the future, we will have LSST going full time. LST will be able to detect and put limits, very stringent limits down to very faint absolute magnitudes of stars in even more extragalactic further distances. So we'll be able to build bigger samples of these precursors before explosion, and maybe even take spectra before explosion and say this star is going to go supernova. So these are kind of the differences even in just absolute magnitude space that we're working with. So this is the type 2 that had a precursor that was very luminous and it went off as a type 2. This is just the optical limits from a type 2 supernova that did not do anything too crazy, but did actually have a very luminous light curve as well. So a lot of diversity here that we need to fill in, connecting this point of life to the point of death. And I think LSST is really like the future for that. So moving a little bit into the supernovae itself. Once the supernova goes off, what are we actually sampling and how can it tell us about the late stage evolution of red supergiants? So again, this confined circumstellar material, the stuff that's right around the star before it explodes, it tells us about late stage stellar evolution because that is the stuff that is ejected during these phases of late stage burning, carbon burning, silicon burning, oxygen burning. It can tell us about the mass loss rate, which is an uncertainty even just in local red supergiants. It can tell us about the progenitor identity. If I get on target early enough, I can understand the composition of the circumstellar material. That can tell me about the metals and the composition of the red supergiant surface and help me understand its identity. It can also then tell us just about basic physics about and very, things that we really needed to know about shock breakout, how shock breaks out of the 3D surface, dynamic shock physics, shock interaction, etc. So this is my kind of cartoon that I'm going to walk you through this phenomenological picture here, where you have the star embedded in CSM, and I'm going to walk through what it looks like observationally as you break out into confined circumstellar material observationally. So the first thing that we've kind of learned is that we have this evidence for shock breakout. Shock breakout is actually a much more extended process if there's CSM around the star. So for a bare red supergiant, shock breakout might last an hour to a day, depending on if you take into account all the 3D effects, because it's a very big star. So the light has to travel to the observer from other sides. And so we've learned that that is actually a very complicated process. But we've seen these really dramatic evolutions of very, very early time, so 0.1 days, less than the day before explosion, from this dramatic color evolution. This is G minus R color. This is relative to first light. And we detected supernovae so early that we're seeing this dramatic change from red down to blue and then back to red. And so what we think this is breakout from the circumstellar material that was usually that was actually pretty dusty. And then as the breakout emission, so these are the first photons that are emerging from the stellar surface, they then don't see nothing. They see more stuff, which is the CSM. That then they have to break out of that. That causes this transition from red to blue. And so we're seeing this constraint on the size and the most local red supergiant CSM. So this is something that is really just starting to open up as an avenue of studying red supergiant shock breakout, because we need to account for the fact that the stellar envelope is not sitting in a vacuum. It's sitting with stuff around it, a lot of gas around it, that then influences the temperature evolution, the radius evolution of the early time supernova photosphere, and then just even the early time temperature and colors. We see this. So the first shock breakout signature there. I think there's a lot to do here, but it requires getting on target very, very early. So this is something that also we hope to explore with LSST plus other high cadence surveys. So LSST will provide very deep images, but very low cadence, meaning it won't observe the same nearby supernova explosion very often. But every once in a while, they will observe or at least have an image of the supernova site, and then other surveys that are tiling the same areas like ZTF. So I'm a part of ZTF, and then other surveys might do the same. They're hitting the same fields intra-night. So the goal is hopefully that LSST provides a detection or at least a very, very deep limit, and then an hour later, ZTF hits the same field, observes a supernova, and then we're observing the first light of a supernova within an hour. So that's the fantastic part of combining surveys. And I think that is the way to leverage LSST, even though it's not meant for fast and young transients, but it's a way to actually explore the phase space that other surveys that just have a shallower depth cannot reach. We really want to get down to these absolute magnitudes that are truly tracing the first hour, first minutes, first seconds of shock breakout. And in order to do that, we need deeper detections that ZTF and other transient surveys cannot do for a larger volume of events. So that's what we want to do in the future. We've kind of explored this recently, and just by serendipity, we detected this supernova within an hour of non-detection. So this is a paper led by my former summer student, Rajula Iti, who is now going to be a grad student at University of Maryland. And so this is for a type 2b supernova, so not exactly a red supergiant, but a red supergiant with a lower hydrogen envelope mass. But this is kind of the observational strategy that I hope LSST plus ZTF will give us in the future. And this is purely serendipitous. So ZTF observed this galaxy in G band, and then 1 hour later, there's a supernova in I band. It's like completely serendipitous. We didn't mean to get this, but this is definitely like a very, very beautiful constraint on shock breakout in type 2b, and it's one of the earliest detections of a supernova to date. And this is something that I hope we're going to do systematically with LSST in the future. This paper has a lot more components. If you're interested in UV spectra or anything like that, there's a lot more in this paper if you want to talk to me about that. But I just want to highlight from the shock breakout side, this is what we want to do in the future. So if I surround my red supergiant in a lot of confined circumstellar material, and then I break out into it, I'm going to actually see a very, very interesting observational signature. So this is the optical spectrum of what I expect if I could observe something within 0.3 days of explosion. It rarely happens, but something that maybe we can do more frequently in the future if I'm actually able to see that rise of a supernova from a very deep detection depth to something that's rising a magnitude in an hour or a couple magnitudes in an hour. So that first breakout signature. And so you see all these high ionization lines. This is actually direct evidence of the circumstellar material. My shock wave is heating up to extremely high temperatures, and it's photoionizing. It's continually ionizing the stuff ahead of me because my shock breakout burst has all of these like hard X-ray photons that are breaking through all of this circumsolar material, and it's providing this signature of the recombination of the ions that are in that circumsolar material. This is a direct tracer of the composition of the CSM, which is a direct tracer of the composition of the red supergiant surface before it exploded. Because it's the same stuff. It was on the surface, it got put into the environment, and it's extremely dense. So my shock wave is able to photoionize the stuff ahead of it and provide this beautiful observational signature. But even at 0.3 days, that's really early to get on target. But if my CSM is dense enough, as my shock continues to move outward, as my red supergiant now liberated expands as this type 2 supernova, I will continue to see these high ionization lines. We call them flash features or 2N-like features, and they will persist as long as my CSM is optically thick to electron scattering. And so if I'm an observer, and now we want to do this kind of more routinely, at a day after explosion, we can see these signatures of the shock, photoionizing this material ahead of it. It can give us constraints on the X-ray temperature of the shock, it can give us constraints on the CSM density by looking at the line profile, and it can give us constraints on the composition of the CSM, which then relates to the red supergiant's even metallicity. After a while, it will then reach a point of the CSM that is no longer optically thick. These lines will fade away. That will tell me the extent of the CSM that is that high density. And then the shock wave will transition into a lower density material environment. And my photosphere, where I'm forming my lines, will then recede, and I'll start to see the signatures of my supernova. I'll finally get to see the broad features, 10,000 kilometers per second broad features of my type 2 supernova that then we can observe. So this is an independent constraint on the size of my dense CSM that was created in the last decade before explosion. So this is something that we try to get pretty routinely with type 2 supernovae. We try to build spectral sequences where we see these high ionization lines. These are now observations, and we want to see this transition point. We want to see where the lines are still prominent, and then they transition away. And then this is the point where the CSM becomes optically thin, and then we've reached the look back time, so 6.5 days, then multiply it by the shock velocity, and then the look back time you can get from that. And you can understand how long before explosion was this dense CSM created. This is something that the red supergiant was doing in an enhanced state before explosion. But I just want to point out that if we look at two type 2 supernovae at the exact same phase, they can be very different. Not every type 2 supernova shows these high ionization lines. It's actually something that is pretty recent in the history of red supergiant explosions, is the understanding that these high ionization features are there at a couple days after explosion. So in blue are two objects that have these ionization features. Then this is the model that I was showing you. Then this is an object observed at the exact same phase. They then evolved to look almost identical as a type 2 supernova with these broad features. They definitely all come from red supergiants. And yet one has very high density CSM that it collided with, and the red supergiant created before explosion. And yet the other one did not create even orders of magnitude close to as much CSM density. And its mass loss rate was orders of magnitude less, probably. So why are two red supergiants exploding, two different types of red supergiants exploding with such different mass loss behavior before explosion? That's a fundamental question that we're only just starting to look into now, and the frequency of which then tells us that some red supergiants, some n number of red supergiants explode with high density CSM, have enhanced mass loss, and then others are very quiescent. What is different about cell evolution between these two populations of type 2 supernovae? So that's something fundamental that we want to continue to answer in the future. So yeah, I showed this transition. This is extremely, as you may have noticed, we need to get on target within a day. So I need to be at least awake, to trigger my observation. If ZTF detects it in the night, if I wait till the morning, I may not get a spectrum for 24 hours, 48 hours. So within ZTF and with the amazing work by Nabil Rahimtullah, who's a grad student at Northwestern, we've started to automate this process. So fully automated triggering of spectra and even UV imaging with Swift. So ZTF will detect a new supernova. It will then go through our processing pipeline. It will then have a bunch of quality cuts applied to it. If it passes everything, we are focusing on nearby galaxies. So if it's a nearby galaxy, there's a non-detection, it is young, all these things. If it passes all of our filters, It's then triggered automatically for spectra at Palomar. It's then triggered for spectra automatically at Gemini and SOAR. And then we can also now trigger SWIFT, when SWIFT was still active, to get UV imaging within 6 minutes of that trigger. So this is one example where there's these high ionization features. We caught this at a day. SWIFT was triggered 6 minutes after ZTF observed and filtered the source. So, I mean, this is really, I think, a future promise for young supernovae because, I mean, we're all fully asleep when this happens. So, I mean, there's nothing that can really beat a machine that does this routinely. And so I think that, we're going to want to at least get the first spectrum through automation, and then we can build a spectral sequence through our, approved programs to see the duration of these features, maybe see some early signatures, etc. But the UV is so fast evolving for sure that this is something that through automation is fantastic. So I kind of already presented this quandary, but what is so different about these CSM interacting type 2s, and what does it tell us about late stage red supergiant evolution, enhanced mass loss, shock physics, etc. So that's really the fundamental question that I've been working on in the last 5-10 years. The one thing is that these objects are extremely bright in the UV. So in red are all the objects that show these signatures of CSM interaction. In black are objects where there's no signatures of CSM interaction, but they're all type 2 supernovae. They all look the same on their plateau effectively. And yet there's, for the same type of star, there's orders of magnitude difference in flux in the UV for sure. So they're brighter, they're longer lasting. It's all really connected to this CSM interaction because I get that extra power source from my interaction from the red supergiant being expanding and in its type 2 supernova and colliding with CSM. So that gives me an extra boost of luminosity. And you can see these statistically significant populations of the CSM interacting type 2s and the non-CSM interacting type 2s. And this is really a result of this high density CSM. So these are observational features that we have to think about for type 2s at early times because they truly really affect the early time light rates for sure. When you apply models to try to understand some physical parameters about this CSM, so I take my early time spectra and I try to match it with some radiative transfer models that predict the signatures of this interaction as a time-dependent effect. This is with the non-LT CMFGen code. And then I extract the mass loss rate and CSM density. You see that there is actually a continuum of late-stage mass loss in type 2s. Some have very weak mass loss, some have very strong mass loss. And this is kind of expected because some show these ionization lines and this evidence for CSM interaction, others do not. So this is really a direct connection to the CSM density, very confined around the red supergiant. I hesitate always to say mass loss. It's kind of a loaded term. Is this stuff that is actually truly liberated? Is this stuff that's kind of in more of a cocoon that's going out to large distances and falling back? There's a lot of theory that needs to be kind of solved here. But the earlier we get on target, the better we can understand exactly the composition and structure of this CSM around these type 2 supernova progenitors. Beyond the early time phenomena, the actual light curve plateau, so when it's actually in its recombination phase, post exit of the CSM, these objects are also different. They show brighter plateau luminosities, and they also decline faster. So they have a sharper slope, and they may potentially produce more nickel 56 as explosions, but they're definitely brighter on their plateau. This is potentially related to a couple different things, but I think we're still just trying to understand what is the difference. But the plateau luminosity can give you an indication of the progenitor radius, as well as the ejecta mass and the explosion energy. Assuming that they're all kind of the same explosion energy, this would then imply, if they're brighter on their plateau, a larger progenitor radius and a lower ejecta mass. And so breaking that down, that kind of actually maybe is consistent with this picture of red supergiants that have lost a good amount of material before they explode. So their total ejected mass is lower because they've already removed a lot of their envelope. And potentially they're inflated stars because they've undergone this late stage kind of maybe pulsations or eruptive material. So in order to stay in hydrostatic equilibrium, they might have had to expand. And maybe if this is a binary interaction scenario, they would have expanded anyway already. So this is looking at these same supernovae at later phases. We can then also pick apart what is the unique properties of their red supergiants before exploding. So continuing to follow these events and sub-classifying is really essential, I think. We can also try to understand the red supergiant mass, or at least the helium core, by looking at their late stage spectra. These are called nebular phase spectra. So once the ejecta becomes optically thin, we can then peer into the core of the supernova and see forbidden features that arise from the last burning phases. So oxygen, calcium, iron group elements, and stuff like that. Even nickel if we're in the infrared. And so if we match these to models, we can potentially extract the progenitor zero age main sequence mass, or at least maybe the helium core mass, and then put them on the same plot as the red supergiant mass loss rate that I inferred from the early time spectra. And what I think is, this is a completely biased sample. This is not volume complete or anything. This is just the availability of the literature where we have early time constraints on the CSM and late time constraints on the progenitor mass. And so for this sample, and also any uncertainties in the modeling is obviously a big part of this. But putting this all together and like swallowing the assumptions, we can see that for a variety of red supergiant sizes, we also get a variety of mass loss rates before explosion. So I would have expected that the larger red supergiants would have the higher mass loss rate, so a 1-to-1 relation, maybe. That would be a nice single star picture. But clearly there are objects where there is a very, very high density CSM around them before they explode, and yet they're consistent with lower mass progenitors. That's something that probably single star evolution can't explain. And this is something where you need multiple channels for mass loss, binary interactions, and that. So this is pointing to multiple mass loss mechanisms before explosion. I think that's really fundamental and interesting just in general about the population of red supergiants in their last decades to centuries before explosion. So the last thing I'll talk about, and I've been getting into this a little bit more lately because we've had such fantastic events that are so nearby, is that if you take a type 2 plateau light curve, so this is the rise to peak, this is the plateau, I've kind of truncated the scale. It then falls off once the envelope fully recombines, and then it should be powered by the radioactive decay of nickel-56 that's in its core. So every supernova creates some amount of nickel-56. Mostly 1As, contribute in the universe to all the nickel-56, but type 2 supernovae also make a little bit, and their light curve should be powered by this radioactive decay for eternity. There are other decay products as well, but for objects that are nearby enough, we can wait long time, maybe 2 years or so, and then we can see a transition point where it should have continued to fall off, but now it's actually plateaued into something where an additional power source is contributing to the late time luminosity of these type 2 supernovae. So what is this? So it's actually just the CSM that is at larger radius, and I don't actually need very much of it to power my supernovae at these faint luminosities, because I'm just converting the kinetic energy of the shock into radiation for some amount of CSM density. And if I, have a, even semi-efficient shock, I can create a luminosity that is sizable. And the issue is that we stop observing type 2 supernovae around here. So we never really understand how many of them start to become what I call shock powered. So they are a full interaction powered system. They are not powered by radioactive decay in any significant way after a couple of years in these events where they've plateaued off. So this is one very nice event, 2023 RIXA. Many of us have worked on it. And you can see this complete shift in its line profiles and its transformation as it morphs into this shock-powered thing. It's basically become a supernova remnant at this point, but it's in its infancy. It's a young remnant. And so you have these forbidden lines that I talked about sampling the core. But these lines are powered by radioactive decay. As the radioactive decay falls off, it drops off as my power source. I emerge with something stronger. Then the profiles morph into these boxy profiles that tell me about the shock front, tell me about the shocked region, tell me about even dust formation. I won't get into that exactly, but this is a complete transformation, and this is more what supernova remnants would look like over time, because they are fully powered by a shock. There's no additional power source anymore. And this is a really cool thing to study if we can observe objects later, because this is now sampling millennia before explosion. This is, my shock has moved out to 10 to the 15, 10 to the 16, 10 to the 17 centimeters, 2, 3, 10 years after explosion. It's now sampling what the red supergiant was doing during carbon burning phase. So very, very late time evolution, but still stitching together where we see red supergiants evolving in the Milky Way and stuff in helium burning into the carbon burning phase, which is this last 1,000 and 5,000 years. So it's still something that we can, empirically constrain that they can inform our stellar evolution models. I'll say panchromatic one time in this talk, and then this is the panchromatic spectrum that I think is the future of these nearby events, where we go from radio emission that samples the front shock. This is non-thermal emission from accelerated electrons. So I don't typically work too much on the radio, but I definitely like to work on how the X-rays then get reprocessed across the electromagnetic spectrum, because the X-rays are really the source of this late time shock power. The shock front is very, very hot. It's cooling via thermal Bremsströms. It's thermal emission, but it's primarily emitting an X-ray spectrum. The X-rays then get reabsorbed into the ejecta on both sides of the shock front. I'll talk about it in a second. And then it gets reprocessed as this beautiful multi-wavelength spectrum. So at late times, we really want to understand from far UV all the way to mid-infrared. And so we were able to do this for this nearby event 23XF. I think future events, this is what we really want to do. But, it's not something that we can do all the time. We need something so nearby that we can observe it with JWST, HST, XMM, nearby things, VLA, etc. So what is the physical picture here, just to summarize? It's a bit complicated, but you have stuff outside of your shock. You have stuff inside of your shock. This is the ejecta that is now, very, very weakly powered by radioactive decay, but it's more so powered by the fact that the shock is running into wind from the red supergiant at large distances. This stuff can power your shock to emit X-rays that are, luminous enough, energetic enough to then deposit energy behind your shock and ahead of your shock. This is your reverse shock, and then thermalize stuff in the dense shell in the interaction region. So this is a picture of a hydro simulation where this is your forward shock. This is the stuff that's sampling CSM that's like up here, if this was like in radial space. And so this is the cause of radiosynchrotron emission. You accelerate electrons up here, and then you emit some adiabatic X-rays, maybe non-thermal X-rays, and radiosynchrotron. Then inside you have stuff that's been swept up into this post-shock region, and then you have stuff below the shock, the reverse shock, that's being swept up into this region. It's a very hydrodynamical, very Rayleigh-Taylor unstable region. It's very interesting. But we're actually being able to sample this in nearby supernovae that are not technically galactic remnants, because we're seeing fully shock-powered objects. And so the X-ray emission that I care about is the reverse shock, because this is stuff that's still radiative. It's still able to cool faster than it can expand and dump its power, its luminosity, into the stuff ahead of the shock and behind the shock. And that's why my spectrum looks like this shock-powered emission. So I think that's kind of the picture that we're picking out here. For anyone interested in shock physics, I think this also has really dramatic implications for what is the efficiency of thermalization. How much radiation can I actually dump into a shock front and reprocess versus get out? It's something that people only ever really worked on with supernova remnants. This is something that we can now work on with extragalactic supernovae as well. Because if we have a complete picture of the whole SED, and I kind of understand how much X-rays get out, then I can understand how much has been thermalized, turned into my UV through IR radiation versus gets out as X-rays. So there's some implications there that I think are really interesting in the future. We want to do these panchromatic models as well. These are non-LT radiative transfer models that are starting to cover from far UV all the way to mid-infrared to see if we can do a complete time-dependent picture. So this is work with Luc Dessart, who is putting together time-dependent models that include shock power, radioactive decay, and even dust emission. I put dust in my supernova and see the effect of newly formed dust. We think that type 2 supernovae, especially type 2 supernovae, in my opinion, that have these confined CSM, are probably contributing to the dust budget of the universe and maybe forming a lot of the dust that contributes at even high redshift. So I think that we should all be looking for CSM interacting supernovae as the way to, contribute to the dust budget in the universe, because they can actually form dust and retain dust potentially for many, many years and contribute into the ISM. For anyone interested in X-rays, my student Ferdinand wrote this package called XMAP. It's a very simple X-ray analysis pipeline. X-rays are a bit intimidating, even though we really work with like 5 photons at once in our SED. But if you want to take an X-ray observation, model the spectrum all the way end to end, you can check out this package. This is something that then can tell you the CSM density profile, because X-rays tell you about CSM density. These are the CSM densities inferred from X-ray observations for type 2 supernovae, and it can tell us about mass loss history at larger shock radii. So just something cool that we use the X-rays for and modeling packages. So it's a nice thing to also get X-rays as well. The kind of last thing I'll touch on is, why are not all type 2 supernovae shock powered? Shouldn't every single type 2 supernova become the shock powered system? And why are we not seeing all these just like continuously flat type 2 supernovae in their light curves for forever? Well, I think that this is a question that maybe LSST and Roman and maybe Euclid will answer, because the absolute magnitude of this now transition point could be very, very faint, and maybe it's just out of range, out of depth for a lot of the ground-based time domain surveys. So we just never really know when a type 2 supernova becomes shock powered. We tried to have some HST programs where we looked in the UV and the optical for some shock powered systems. So we're working on analyzing that all. But the real interesting thing is that some are shock powered to some luminosity and some are not. Do some have such weak mass loss rates that they can't even sustain an absolute magnitude or luminosity from shock power that is even detectable by a space-based telescope? That's really interesting. That means that some red supergiants in their last 1,000 years are very, very weak in their mass loss, and some are significant enough. And I think that we need continuous all-sky coverage to just find these and data mine for type 2 supernovae that continue to persist, with LSST for sure. And then that gets you down to 24th magnitude, and then you get Roman and Euclid and other telescopes that are doing all-sky surveys where you can find these and pick these out. So what is the future of all of this? I've kind of talked about everything from before explosion, early time spectroscopy, early time stuff. So to understand supernova precursors, that was the first part of what I talked about, and their progenitor stars. We need LSST for sure to be looking continuously and finding low luminosity gap transients that can probably turn into supernova one day. Roman will do the same. JWST, we need JWST to image more nearby galaxies to get a better coverage of red supergiants that then eventually will become supernovae. And we can get a complete SED and model their dust properties before explosion. Rapid spectroscopy, so in the era of LSST plus ZTF, we can do automatic triggering as well as intranight triggering and intranight detections. I haven't talked about it today, but if anyone is interested in what is happening with UV spectroscopy, I'm part of the UVEX team. That will be the next mission for NASA to do far UV and near UV spectroscopy of up to 10 young 4-cloud supernovae is one of the mission goals. And so I've tried to do that same science with HST. It's very hard. If anyone wants to talk about that, I'm happy to chat about HST UV spectroscopy. It's a lot more difficult because it's not designed to move so rapidly at early times. But UVEX will do that. Swift, I hope, will be reboosted, and we'll have this auto-triggering capability again, and we'll continue to have our ultraviolet light curve sampled. For late time shock power, continue to use HST in the slow, more manageable mode. JWST, Roman, Euclid, Chandra, XM, all these multi-wavelength facilities are how we understand shock power. We can't just look in one wavelength. We should be looking across the electromagnetic spectrum to understand what is the emergence of shock powered emission from CSM interacting supernovae at later times, much later times. And so to kind of motivate this a little bit more, what is the continuum of red supergiant mass loss during late stage evolution? These are the observed in gray red supergiant mass loss rates from either the Milky Way plus a local galaxy from this study compared to red supergiant mass loss predictions for a model. But I think what's more interesting is just look at the observations of red supergiants during their helium burning phase. And you look at the mass loss rates, very low. And then we know that just from some supernovae in the last 1,000 years of explosion, it ramps up to almost 10 to the minus 4 solar masses per year. That's a couple orders of magnitude, sometimes even 5 orders of magnitude. And then I showed you mass loss rates that are even up here, like off the plot, in the last 10 years before explosion. So red supergiants, all these stars eventually become the supernovae that I've talked about today. And yet there's very different mass loss rates depending on their evolutionary picture. So something very dramatic happens in these massive stars, in these very common supernovae, before explosion. And it's something that we really need to think about for evolutionary codes, for our understanding of the ISM, our understanding of supernova contributions. So, with that, yeah, I'll finish. Thank you.
Thank you very much for this great talk. Any questions? Yeah.
I'm sorry to be the geologist asking geology questions,
Oh, please.
but what sort of signatures would you expect to get embedded into those dust grains that may eventually become part of another solar system that we might look for in primitive meteorites?
Ooh, I guess that's a lot of probably time between getting the dust grains out of the supernova, back into the ISM, then back into molecular clouds and planetary. I think that what's interesting about these dust grains is that they are diverse in that they are composed of both silicates and carbonaceous and graphite. I guess graphite. Yeah. So silicates and graphitic carbonaceous grains. And I think that we need to understand the contribution from both, because the silicate grains probably come from the innermost core of the supernova, because that's where you can get silicate at. That's where there's actually that stuff. Versus carbonaceous grains, maybe that's more of the stuff on more of the surface of those. So that's just one avenue that my mind goes to, where we're looking for silicate composition, and if we can understand the amount of silicate dust grains that are creating a supernova, and then you have a constraint from, say, even ISM dust or molecular cloud dust from silicate composition, can we then map that to supernova dust yields? It's something maybe like in the future we'll have a much better constraint, because I think we're just trying to understand if supernovae are creating dust or if they're dusty because there's dust in the environment. Like the study of dust in supernovae is actually really in its infancy, because Jadovsky is really just breaking things open for us and understanding that like all supernovae are infrared bright because of dust, and we're just trying to understand how much they're even forming. But local supernovae like 87A have formed of a solar mass's worth of dust, a mixture of silicates and carbonaceous grains, and maybe also the grain size is essential. If we can understand what was the size of these grains, and then how much by grain size do they then contribute to, I don't know, like pebble growth and stuff in exoplanets and stuff. I'm just thinking, I'm just spitballing. I think it's fantastic. Yeah.
And just a follow up, based on beryllium-10 and other fairly short-lived radioisotopes, we kind of in our community come up with the idea that a supernova explosion could actually trigger the collapse of our planetary nebula, and then potentially, so there would have been an injection of material into what eventually became us.
Yeah.
And if we're trying to nail down what type of supernova it is, if we would look in the isotopic signatures of the silicates, for example.
Potentially, yeah. If you saw an enhancement potentially from different, I mean, you're going to supplement a lot of your dust from the supernova radiation as well. But yeah, the kind of common picture is that the core collapse supernovae from massive stars are the ones creating most of the dust. The type 1A supernovae are creating less, but they could potentially, as remnants, create a lot of dust as well. But different compositions. Because they have so many more metals in the type 1A supernovae, they will create a much different signature. Yeah.
Thank you.
Yeah, that's super cool.
Question?
Thanks, very cool. This plot, so it's like 1,000 years before explosion. This massless rate. When is this supposed to be?
These gray dots are from local red supergiants. Yeah. So these are probably at least 10,000 years from explosion. So they're in their healing phase. So these are observed red supergiant massless rates. And then this, I just put a line to show what we learned from just some supernovae as their massless rate in 1,000 years before explosion. Just to kind of illustrate that is much higher than the red
Yeah,
supergiants that we observed. Yeah.
So it could be that like from, I don't know, 10,000 years to 10.
Yeah.
It might jump from 10 in the -8 to 10 in the -2, like you said before, right?
Yeah. The potential, yeah.
And I guess there's something we don't know what happens and if it's extreme things.
Exactly. Yeah, and I think it's relevant to pose that question, because say this is my population of red supergiants that I'm pulling from, and half of these red supergiants then will make type 2 supernovae that have dense CSM, because now we're understanding the fraction of type 2 supernovae with dense CSM, because we observe all of them in a volumetric sense, early time explosion, like right after explosion. Then half of these stars have to then evolve to have massless rates up here before they explode. How do we do that? We need to know.
Thank you, Professor. When you discuss the non-correlation between the progenitor mass and the massless rates, you mentioned something. This one.
Yeah.
You mentioned that there could be other masses that would rather than normal.
Yeah.
And do you think they could be traced by some asymmetries in the interaction maybe, or having that at the beginning, because those satellites may not be that could be something.
Yeah, absolutely. I'm showing a pretty normal nebular spectrum, but there's nebular spectra that we see that are very complicated in their H alpha profile. And so we know those are interacting. What is the CSM structure that's interacting with? I'm usually one not to invoke asymmetries until I understand the dust, because the dust is why, dust is messing up a lot of things. Like these profiles are asymmetric in H alpha, because this side is being eaten away by the fact that this is super bright in the infrared from dust. There's dust where this line is forming and it's cutting this away. And so without dust, this might look like an asymmetric CSM picture, but I can't constrain that necessarily, because I also have to factor in the dust attenuation as well. But yeah, I think that if we build a sample of these late-time objects with more and more complicated H alpha structures and line profiles, and then we also have a constraint on how much dust is potentially eating away at our profiles, then we can say the CSM is there and it's also asymmetric, or it's there and it's symmetric. Yeah, I agree, 100%. Yeah.
Great talk. So you talked about the possibility of having a light curve with LSST and ZTF with 50 megaparsecs or whatever, that number they count there. But there we don't actually resolve the star, right? So we just see the post and we have a light curve of everything plus the progenitor. So I'm trying to understand what's the limitation with the fact that we cannot actually see the star. We see a group of stars there doing something, and then after the explosion, we will also lose the star.
Yeah.
But in all cases, it's not a direct reflection.
Yeah.
So this seems like a great way of increasing the numbers of progenitor constraints, but it's not the same as actually with HST or JWST looking at the star.
For sure.
Can you maybe elaborate on the difference?
Yeah, so for the young supernova side, I think we're okay, because I want LSST to detect something that is a young supernova at -10, -12. That is brighter than a red supergiant in its quiescence. Like that's brighter than the star that exploded. And then I want ZTF to detect an hour later when it's risen to 14 times. I'm just like showing an illustration of some nearby events where this could be possible. Like LSST detects this point, ZTF detects this point. At this absolute magnitude, I'm resolving a source in an extragalactic galaxy, but it's so bright that it's comparable to the brightness of the galaxy, so I know that it's a supernova. But for the precursors, for stuff that is like the star doing something before explosion, I have to be very careful with LSST not to use the difference imaging to take it too seriously, because I'm taking a template, I'm subtracting off what is then, I'm taking an image tonight, I'm subtracting out the template, and I see a transient that is low luminosity, that might be a precursor. But I'm actually, in the template, there's a star, there was the progenitor. So I've subtracted off the progenitor. So it's something that we have to think about with LSST. We want to do more precise photometry of just the region where the transient is and confirm. So I didn't talk about this, but we have we've built pipelines that were first based on pan stars. Now we've adopted it into LSST that have more robust algorithms for confirming that a source is a true detection. And it's something that we'll apply to LSST and test and make sure that these are really low luminosity precursors and they're persistent transients. And it's not just a host galaxy like star forming region or something like that. Yeah, but I will get you a precursor light curve, and maybe I'll get a precursor spectrum of the star, doing something enhanced at some super Eddington luminosity potentially, but I will never be able to resolve the stellar population around at that source. It will just look like a grouping of pretty big pixels compared to HST, because it's like arcsecond pixel size, 0.7 arcsecond. Then maybe one day we can have a follow-up program with JWST or HST to then go back. Once the supernova has gone off, goes away, we look at the stellar population again. But yeah, I think maybe there's a little bit more hope with Euclid and the small field of view that Roman will observe, because it will have a much better PSF. And so you could actually see that one star is getting brighter, and you could resolve that star. It's like having an HST observing a wider field of view. So it's not something that LSST will do, but it's something that maybe Roman can do.
Now that you're here, how do you find the first light? Because here I would say that the first point of the red one, that could be the first detection of the supernovae, and then the first light is before.
Yeah.
So how difficult it is to estimate the first light with this one?
Showing these objects is like maybe kind of disingenuous, because these are the earliest type of supernovae we probably ever observed. And the first light is estimated based on just the difference between this and the last non-detection, which is down at fainter magnitudes. But most sky surveys have a limit here, and they detect something here, and then the non-detection's here. And then we say, oh, the first light happened in between there. We are so biased. We're so uncertain about what is first light with young supernovae, because we have two observations with telescopes that are 1.5 meters or 2 meters, and we just literally cannot get to the depths. But these objects were so nearby that we could sample these low luminosity regimes. So first light really needs a constraint from a deeper telescope like LSST. But if I see something that is detected at -10, that's probably within a couple hours of this. Like that's an absolute magnitude that's so faint that it can't be within a day. Like maybe, I don't know.
Okay, but this also changed the picture that we have about flash lines.
Yeah.
Right?
We might have a time scale that's off by a day or half a day. Yeah.
So what is the fraction of flash ionized supernova right now?
I would say it's like approximately 30% to 40%.
And do you think the number is larger? The fraction is larger?
Possibly, yeah.
Because, for example, for 17 WE, that you showed. So you show that there is no flash line, but if you believe that if you have a deeper observations, probably the explosion was before. So that epoch will be later than expected.
Maybe like half a day at most. Yeah.
Half a day?
Yeah, maybe. I would say hours, maybe.
Okay. So
17 AW was so nearby that I think we were very much on target.
Okay, but based on all these analysis that you did, you expect a higher number of
potentially. I don't think we have we're working on the final number, but 30-40% maybe. Yeah. But I don't need the most precise constraint, because I can have all my flash line timescales have an uncertainty, and that's okay. So this is 2 days and there's nothing. This is 2 days and there's something. That means that this had dense CSM and this didn't. So maybe this is off by 0.3 days or half a day, but it still means that this red supergiant did not have dense CSM at approximately the same shock radius. So these are very different, and these are long lasting. These will last a week. So if I don't see anything for a week, I know that this thing is not interacting. So you can definitely constrain between two very extreme populations: the very bare red supergiants and the very densely enshrouded ones.
Another funny question. Do you expect that the flash ionized supernovae show signatures of interaction at late phases?
Yeah.
All of them?
Yeah.
So,
most of them have a higher plateau luminosity, and many of them have a shorter plateau. A significant fraction of them do have this late stage interaction that is strong enough to make these boxy profiles and turn into a shock powered supernova. But I don't think we have a good understanding of how many, like 1 to 1. We've this is work ongoing, but for every single flash ionized supernova, we've gotten late stage nebular spectra with Keck for 1 year, 2 year, 3 years, and they're very diverse. Some look completely normal, some are completely shock powered. So what the larger distance CSM is very uncertain.
no question. Mine.
Very quick follow-up.
Sure.
So you mentioned here 34%. Do you find a spectrum between the ones that show CSM interaction, the ones that don't? Do you find the two that
Continue.
small?
Yeah. So that was the first study we did on this, and there are ones that have these persistent features for almost a week. There are ones that have the persistent features for only 3 days, 1 day, 2 days, maybe a tiny signature of it. And then, when we modeled them, this is what I was showing here. Yeah. These are the stronger interacting ones. These are the less interacting ones. These are the almost no interacting ones. And so just in terms of the duration of the line profile, these ionization lines, and then the constraints on the CSM density, we hypothesized that there was this continuum where there was strong, weak, strong, medium, and weak. So there's very huge diversity.
Okay, so let's thank Wynn again. Wait for him for the pizza, please. Thank you. Alba. Alba.